So the spectral theorem tells us that symmetric matrices are the only ones that have orthogonal diagonalizations. If I take my symmetric matrix, I know that I can write it like this, and I'm going to try to come up with another representation that's going to shine some light on what exactly this matrix is doing in terms of eigenvectors and eigenvector basis. Now remember that our matrix Q was filled with our orthogonal and orthonormal eigenvectors. So this is an orthogonal matrix. Corresponding to each one of those is going to be an eigenvalue on this diagonal matrix. Now remember, the first column of Q gets assigned to the first diagonal entry of D. And then over here, we're going to have the transpose of our orthogonal matrix. So basically taking all of the columns and writing them as rows. And let's just say I multiply it by some vector x. So I'll put it here. Now to come up with a very interesting way of writing things, I'm going to talk about multiplying these things and then these things separately, just so you can see what's happening here. So we know that in this first instance, if we've got the definition of a matrix times a matrix, it basically says, okay, take that first matrix Q and then multiply it by the first column of that second one, and then do the same thing all the way down to the others. That's the definition of a matrix times a matrix, the theoretical one, which is really, when we talk about things like this, the way to go. And in that second instance, what is going to happen here is we just have our dot product, first row dotted with x, and that's going to go all the way down to last row dotted with x. Now, by definition of a matrix times a vector, the first entry is going to weight the first column here. Well, all of these entries are 0 except for the very first one. So the only thing that's going to survive from this matrix vector product is going to be the first weight, lambda 1, times the first column, u1. Everything else is going to be 0. Now in the same thing here, we're going to get lambda 2 times u2. And in all of these instances, the only thing that will survive will be the column of Q that has the weight lambda n. I can write this dot product version as u1 transpose times x all the way down to un transpose times x. Now, it's the same idea as we just finished talking about. We have a matrix times a vector. So if I take a matrix times a vector, I take the first column of the matrix and I weight it by the first entry of the vector. It doesn't really matter what order I write them in because this is a scalar. So I will write it like this, vector times this scalar, and it will go all the way down. I'll weight them all like this. And what you'll notice is that every single one of these things has an x multiplying on the right. So I can factor it out. And when I factor it out, I'll get something that looks like this. And remember, this is what ax is supposed to be. So if the x's are the same, that means the a must be this thing right here. And this is called the spectral decomposition of your matrix A. What we are doing is taking it, and because it has orthonormal eigenvectors, we are breaking it up. We are decomposing it into parts that are related to the spectrum or the eigenvalues. And we are saying, look, this matrix, which is symmetric, so if you have your real symmetric matrix, then you can write it and decompose it into these constituent parts. And they're all related to eigenvectors and eigenvalues, but there's a deeper interpretation. A piece that looks like this is very much related to something called a projection. So when we talk about projections, what we're saying is the following, right? We've got some vector u, and it makes its own subspace. So if I were to take a different vector, let's say x, and project it onto that subspace, I'm basically trying to talk about the shadow of x, this thing x hat. So we've talked about this. X hat is basically just going to be x dotted with u dotted with u, times u. If u is unit length, then u dotted with u is just 1. Its length is 1. And that means we are able to write this x hat as x dotted with u times u. And then we can reorganize this a little bit, right? We've talked a lot about this. We can say that this is u dotted with x with a u. This is just a constant, and because it's a constant, we can switch the order around and kind of write it like this. And we can now use this dot product notation. We'll say that this is a u transpose times x. And what I've got here is that this projection is given by u transpose on x. And that's the key here. These things are what we see in that spectral decomposition. This is called the projection matrix. M is equal to this thing, u times u transpose. This matrix will project x onto the subspace span of u. I should say the subspace spanned by u. Now, in this case, that subspace is a line because there's only one vector. And now, that's the whole idea. When I have this spectral decomposition, remember that each one of these things each one of the u's was an eigenvector. So the spectral decomposition says, look, we are going to take some vector x and project it onto each eigenspace. Then we are going to add up these projections. That's what the matrix does. This is what A is doing. When you've got an orthogonal diagonalization, it's taking a vector. When you act on a vector, what it's going to do is automatically split it up into a whole bunch of orthogonal projections and then add them all up. So if I have this matrix A, it was symmetric, and we found that it had two eigenvalues. It had lambda was 2, and that lambda that was 2 produced this eigenvector 2, 1. We normalized it to get 1 over root 5, 2 and 1. We have the lambda equals -3. Its eigenvector was 1, -2. And because these are eigenspaces, we can, and there are infinitely many bases, we can just normalize them. And that will be the one that we want. So 1 over root 5 in here. So clearly A is symmetric, and that means it has to have an orthogonal diagonalization. So it has to be able to be written like this. And if you want to actually put it all together here, we are going to take the two normalized eigenvectors, put them in for Q, 2 over root 5, 1 over root 5, so that's U1, 1 over root 5, -2 over root 5, that'll be our Q. Our D It's going to be 2, 0, 0, negative 3. And then the transpose basically flips this around. Now we're very lucky that in this particular case, the transpose of this matrix is itself. So Q equals Q transpose in this particular case. So the spectral theorem says you are going to be able to write this matrix A as follows. You're going to be able to take the first eigenvalue 2 and then go U1 times U1 transpose. Then you're going to subtract or add the second eigenvalue U2, U2 transpose. So in this particular case, you're going to get a 1 over root 5 squared because each one of those matrices has a 1 over root 5. It'll be the 2, 1 times 2, 1 minus 3, 1 over root 5 squared because each of the column vectors has a 1 over root 5. 1, negative 2, 1, negative 2. Each one of these things produces the projection matrix. 2, and then we'll have the following. We'll have 4 over 5, 2 over 5, 2 over 5, 1 over 5, subtract 3, and now we'll build this 1 over 5 minus 2 over 5, negative 2 over 5, 4 over 5. If I take, for example, my matrix A and I multiply it by the vector 1, 1. In this particular situation, I'm going to have 2 U1, U1 transpose minus 3 U2, U2 transpose times this vector X times this vector 1, 1. So I'm going to be able to break it up into these things that I've just finished talking about. 2/5, 2/5, 1/5 here, 1, 1, subtract 3, 1/5, negative 2/5, negative 2/5, 4/5, and a 1, 1. I'm going to do a matrix vector product. I'll get a 6/5 and a 3/5, subtract 3, negative 1/5, and 2/5. My first eigenvector was 2, 1. So the first eigenvector kind of lived here, and it spans some space. So there's the first eigenspace. We'll call it E2 because it corresponded to the eigenvalue 2. The second eigenvector was 1, negative 2. So somewhere down here, it corresponds to this space. So there's the second eigenspace, and we'll call this E negative 3 because it's the the space spanned by that eigenvector. Now, these two lines are orthogonal. Even in my really crappy picture, you can see that they are orthogonal. The vector X that I'm talking about is the vector 1, 1. So it lives right there. What this projection matrix is saying, or what the spectral decomposition is saying, that if I take the matrix A and multiply it by 1, 1, simultaneously two things are going to happen. First of all, this matrix is going to be split up into two projections. So that vector 1, 1 is going to get projected onto each of the eigenspaces. Take that vector and then shine it down onto the first eigenspace. So right there. There, that vector in green represents the projection onto E2. The vector in red represents me shining the flashlight and projecting this onto the second eigenspace. They are orthogonal, so it's really nice. Then, the spectral theorem tells us that each of these components is going to get scaled. So it's going to get scaled by some amount. So this length here is going to roughly double. So that's going to get turned into some value there. This length here is going to get tripled, but be flipped in the other direction. So roughly 1, roughly 2, and roughly 3. So that would be the second component right there. And then the theorem says you add these two bits together. So you can do this with the parallelogram rule, and then your result will live somewhere here. That's what the spectral decomposition theorem is saying. Now, this is just like diagonalization from before. If you want, you can check this. You can check this on your matrix, and what you'll end up with is a 3 and a 0. Hey, that kind of looks like what I've got in my crappy picture there. And that's the whole point. That's the decomposition.